everyone, welcome to another video. Today I will be introducing probability. So first I'll cover what events and outcomes are, and then I'll discuss how to combine events using and or. Then I'll talk about independent versus dependent events, then permutations and combinations, then some probability nomenclature, then some probability functions, and finally binomial and normal distributions. First, what are events and outcomes? So an event is something like flipping a coin or rolling a die. It's you do something and then it can have a certain outcome. So for example, an outcome of flipping a coin is landing on heads or landing on tails. The event is flipping a coin and the outcome is landing on heads or tails. So if the outcomes have an equal probability, which they do when flipping a coin, if there are two outcomes, each outcome has a 1 out of 2 chance of happening. And so equal probability of each unit outcome is very useful when combining them. And for rolling a die, there are 6 outcomes for the event of rolling a die. And because each outcome is equally likely, each outcome is 1 out of 6. But let's say we wanted to find, what's the outcome of rolling 3 or less? Then we would simply add up the outcomes and we get 3 out of 6 or a half. But if it wasn't equally outcomes, we could add it up, but since it is, we can actually instead, we know that there are 3 outcomes, and so we can simply do 3 divided by 6 instead of adding up 1 over 6 plus 1 over 6 plus 1 over 6. What if we want to combine events? So we can use a probability tree. We will combine flipping a coin and rolling a die. So first we flip a coin and we get heads or tails, and then we roll a die and we get 1 through 6. And we see, after doing that, there are 12 total possibilities, rolling a heads and then getting 1 through 6, and then rolling a tails and getting 1 through 6. And we can also make a probability table where there are also 12 probabilities, and each item in the table is an outcome that we could get. We could get 1 in heads, or anything 1 through 6 in heads, and anything 1 through 6 in tails. But how would we actually discuss the outcome for a probability combining events? And that's how we would use and or. So let's say, what is the probability of landing heads and rolling a 1? So the probability of landing heads is a half, and the probability of rolling a 1 is a sixth. And so we can multiply that, a half times a sixth gets us a 12th. And to verify, we can count up the number of the 12 solutions that we landed both on heads and rolled a 1. So this is the only solution where that happens, and so there's 1 out of 12, and so that matches. But what about landing on heads or rolling a 1? And so we could either land on heads or roll a 1 or do both. So landing on heads is 1/2, rolling a 1 is a sixth. So there's a half the time we land on heads, but then the other half of the time we could still roll a 1. So we'll do a half plus a half times a sixth, and that will get us 7 out of 12. So or is generally going to be addition and is going to be multiplication, but with or, to make sure we aren't double counting, we'll have to multiply whatever's left by the probability of the first thing not happening. So we can go over and count. So the probability of landing heads is a half, so a half of the time we land heads, and then a sixth of the time we get a 1. But we don't want to double count this 1h. So we know that, we're only dealing with the half the times that we don't get heads. So we're only dealing with the tails, and that's when we get 1/6, and we would add it to the half of the heads that we already had. And what about landing tails and rolling an even number? So it doesn't just be one outcome, we could have a group of outcomes that we want. Landing tails could be these 6, and rolling an even number is half of them. So for each of them, it's half, and so the chance of landing tails is half. The chance of rolling an even number is half. The chance of them both happening is a half times a half, which is a fourth. But a chance of either of them happening, the chance of landing tails, is a half. But then, if we don't land tails, there is still, of the remaining half of the times we don't, of those times we can still roll an even number. So for this, we get a half plus a half times a half, which gets us 3/4. So generally, and will be multiplication, and or will be addition, but to make sure we don't double count, we will have to multiply it by the chance of not getting the first outcome. And there's also special cases when one of the outcomes is impossible or guaranteed. So if one of the outcomes is impossible, so let's say we said, oh, landing heads and rolling a 7. That's never going to happen, and so this has a 0% chance. So if there's ever an impossible thing in an and, that means no matter what, it's not going to happen. But if it's an impossible thing with an or, so if it's landing heads or rolling a 7, we know this is never going to happen, but this one could still happen, meaning landing heads or rolling a 7, we're really just asking if you're going to land heads. But then if something is guaranteed, so let's say landing heads or rolling something less than 7, then this is guaranteed to happen, so we're really just looking at landing heads, because we know this is happening anyway. And if it's guaranteed with an or, landing heads or rolling something less than 7, we know this is guaranteed to happen, this one doesn't even matter, we know it's happening no matter what, so this will always be true. If any of an or, either of the or conditions are true 100% of the time, the entire condition is true 100% of the time. That's just with independent events. Now let's look at how independent and dependent events differ. So if there was a bag with 12 tickets in them, where 5 of them are blue and 7 of them are red, we want to find the probability of drawing 3 blue tickets. But to show the independent versus dependent, one time will be with replacement and one time will be without replacement. So with replacement, we can go and grab one, we'll look at it and then put it back. So the probability will not change after each draw. But without replacement means that after we go in and we grab one, we will leave it out of the bag, and so what's remaining will have been influenced by what we took out. Let's say we take out a blue one, now there's only 4 blue ones left. So it's not 5 out of 12, it's now 4 out of 11 total. So first let's look at what's the probability of drawing 3 blue tickets with replacement. So there's 5 blue out of 12 total. So each time we draw, there's going to be 5 out of 12. And so it will simply be 5 out of 12 3 times multiplied. And that gets us about 7.23% of the time. Without replacement, first we would go in, there's 5 blue out of the 12 total. We'll grab one of them. But now, after doing that 5 out of 12 chance, now there's only 4 out of 11. And so the chance that we grab another is 4 out of 11. But now there's only 3 out of 10. And so the chance that we grab the third one is 3 out of 10, after 2 have already been removed. So we'll multiply 5 out of 12 times 4 out of 11 times 3 out of 10, and we get about 4.55%. So this just showcases the difference between independent and dependent events. Dependent events, the outcome of one event can influence the outcome of another event, but with independent events, the outcomes do not depend whatsoever on separate events. But now let's go through permutations and combinations. As we saw with the previous slide, we saw the 5 times 4 times 3, and that is something like factorial. So this is the definition of factorial. N factorial is equal to n times n minus 1 factorial, and 0 factorial is equal to 1. What that means is if we have 5 factorial, it's equal to 5 times 4 factorial, which is equal to 5 times 4 times 3 factorial, which is equal to 5 times 4 times 3 times 2 factorial, which is equal to 5 times 4 times 3 times 2 times 1 factorial, which is equal to 5 times 4 times 3 times 2 times 1. So generally, any number factorial will be that times it, 1 less times 1 less times 1 less times 1 less until we get back to 1. And these numbers will grow very, very quickly. But Now let's talk about what permutations are. Permutations is the number of different ways items can be ordered in a list. So for example, there are 12 items here, and let's say we want to order them into 12 slots. So we want to pick first, we would grab one of the 12, so there's 12 options. And then we've already taken one out, so now there's 11 options, and then 10 options, and then 9 options. And so the number of permutations of these 12 items into 12 slots would be 12 factorial. But what if we only wanted 3 slots? So then there's 12 items for the first slot, there's 11 options for the second, 10 options for the third, and then we've filled the list. So it would be 12 times 11 times 10. Another way we could write that is 12 factorial divided by 9 factorial. And so the formula for the number of permutations of n items and r slots will be n factorial divided by n minus r factorial. Combinations, on the other hand, is the number of different ways a set of items can be sorted into groups. So the thing with combinations is the order does not matter. And so we're going to have to divide more to kind of group together things that are different orders but the same groups. So let's say we wanted, of these 12 items, we wanted to put 2 of them, we want to select 2 of them. So we would have 12 options for the first, and then 11 options for the second. But then, we could have gone 11 and then 12, or 12 and 11. And so to account for that, we'll have to divide by 2. And generally, this will be the formula, and we call this choose, so this would be n choose r. So the formula is n factorial divided by r factorial times n minus r factorial. And something interesting about this is that if we have 12 choose 12, then the number of different ways we can choose all 12 of these in a group is 1. It's just putting them all in a group. But the number of ways we can do 12 choose 0, the number of ways we can choose none of them is also 1, just choosing none of them. The number of ways we can choose only one of them is 12 ways, we can pick any one. But the number of ways we can choose 11 is essentially not picking one of them. So there's 12 ways of picking 1 and 12 ways of picking 11. So actually, the maximum value for choosing out of n things is if we choose exactly half, or 6 of them. And 5 and 7 will be the same, 4 and 8 will be the same. It's symmetrical around its center. Now let's go over some probability nomenclature, expected value, variance, and standard deviation. So here we'll look at the event of rolling 2 die at the same time, and you could do a probability tree or probability table and count up the ways of getting 2 through 12. But I did that here and wrote the chance of getting each of the numbers, and we'll try to find the expected value of this event. So the way to do this is to add up for each outcome, multiply it by the probability of that happening, and then add it together. We're essentially doing the mean. If there's 1, 2, there's 2 3s, there's 3 4s, there's 4 5s, etc. We're essentially finding the mean, but instead of using the number out of the total, we'll simply use the probability. So the formula would be the sum for all values of the value times its probability. And so if we added them all up, here we would get 7. And that's because it's symmetrical, we'll get the very middle. If it was more likely to get higher numbers, then it would probably be skewed slightly higher. This is generally just a weighted average of all of the outcomes by their probability. There's also variance, which tells you something about the spread of the values. So the formula for this will be the sum for all values of the difference between the current value and the expected value, but then we'll square it so we don't have positive and negative values. We'll find essentially the absolute distance, and then we'll multiply it by its probability, so times the probability of that outcome. And so this is 5 away, this is 4 away, 3 away, 2 away, 1 away, not any, it's the same value, and then it goes back to 1, 2, 3, 4, 5. And so if we did this operation, we would get the variance of this event is 5.83, or the variance of the value of the two die added is 5.83. And standard deviation, to calculate it, it's just the standard deviation is equal to the square root of the variance. But while the variance just tells us the general spread, the standard deviation actually tells us how far away from the center things are likely to be. So 2.42, so that tells us about here and about here is where most of the data will be clumped up. And we see on the edges there's only about a sixth of it on this side and a sixth of it on this side. So about 2/3 of the data is within one standard deviation of the mean. Now some functions. So as we saw before, that table with the outcome and the probability is similar to a probability mass function. So where f of x, it's going to look like a piecewise function, and so it's easy to put in a table like that. So let's say it's equal to, we'll use a different, so 1, 2, and 3. So for when x is equal to 1, x is equal to 2, and x is equal to 3, this one has a 50% probability, but then these have a 1 in 4 probability. So we could also put that on a graph. So for 1, it's likely to happen, but then for 2 and 3, their half is likely. And for a probability mass function, if you add up the probability of each of the outcomes, you will always get to 1. So a half plus a fourth plus a fourth is equal to 1. Or the sum of all values should get you to 1. And this tells you the probability given the outcome. And the reason we call this the mass function is it's kind of centered on each point. But what if, instead of using a discrete value where we could get 1, 2, or 3, what if we simply know a range and it could be any number in that range, not just whole numbers, but any real number? So that would be a density function. So let's say we wanted, between 1 and 5, there's an equal chance of getting anywhere. And for this, the area of the entire probability function will have to be equal to 1. So this will be more calculus stuff, but generally if we integrate it from negative infinity to positive infinity, the probability density function, this is essentially saying the area under the curve of the entire probability density function will have to be equal to 1. And so if this is 5 long, we will actually say, this would be 0.2. And we could essentially sort these into buckets. So if we're getting from 0 to 1, there is a 1/5 chance. From 2 to 4, there's also a 1/5 chance. And the area under the curve for probability will tell you the whole probability between a certain values. And if let's say we could also have a probability that looks like that. So then for 1 to 2 it's greater, more likely. For 2 to 5 it's less likely. There's other functions we could do. This looks like a normal distribution or binomial distribution. So generally, the function of x will be a continuous function rather than a discrete function like the probability mass function. And then these sums adding up to 1 are something like the cumulative distribution function. So this would be, oh, if we added up all the values, what's the chance that we're smaller than 3? So this will use a capital F. So capital F of x is the cumulative distribution function. And so here for the, if we're still doing discrete, we do, oh, what's the chance that we're 2 or less? And so we'd say, oh, that includes all of this value and all the previous ones. So that would be 3/4 chance. The chance that we're 1 or less is a half chance. The chance that we're 3 or less is guaranteed. So the cumulative distribution function would be 0 for less than 1. It would be a half between 1 and 2. It would go up a fourth between 2 and 3. And then it would reach 1 at 3 and then stay at 1 forever. But then the density function, so if we had this uniform, let's say we had a uniform distribution where each value is equally as likely, when we integrate it, we would kind of add up each slice as we go along, and so we would grow and grow and grow until we reached 1. So this adds up the chance of getting this value or less. Finally, binomial and normal distributions. So binomial tells you the chance of getting a certain number of outcomes out of a certain number of tries, knowing the probability. So let's say we want to flip a coin 10 times, and we want to see the chance of getting 2 heads. So this will tell us that probability. So then, in this case, k would be 2, n would be 10, and p would be 0.5, because there's a 50% chance we land on heads each time. And so this is actually another way of writing n choose k, the combinations, using these parentheses. This formula can tell us the chance of getting, out of 10 flips, getting 2 or 1 or 0 heads or 8 tails or 4 tails or whichever one we want. And binomial distribution will always be discrete. So just like the probability mass function, it's not buckets where it could be anywhere in between. It's specific values that it can be, and we're finding the probability that it is there. And if we, let's say, instead of doing flipping a coin, we're rolling a die, we want to see, oh, what's the probability of getting a 1 2 times out of rolling 4 times. So here, the k would still be 2, because that's the number of times we want to get the outcome. The total number of times we're doing it is 4. And the probability of getting a 1 each time is a 1/6. So in total that would look like 4 choose 2 times 1/6 squared times 1 minus 1/6, so that's 5/6. And that would be 4 minus 2, which is also 2. And this choose function is here because we're kind of, when we do it this way, we're saying, oh, we're getting 2 1s and 2 of anything else. But we don't care about the order in which we get it, so we're multiplying by the number of different ways you could order it. And then, with binomial distribution, if we kept on making n higher and higher, and we're using a 0.5, So generally, if we look at a binomial distribution, it will look like this. It will follow that general curve, and then it will have values like that and that and that. And it will have discrete values that will follow a general curve. But then if we have, instead of 50% each side, let's say we had, oh, it's 1/6, then it would be skewed heavily to one side. So there's a really good chance of getting it if the probability is high, but if it's low, so for this, for rolling a 1, that's really unlikely. So it can also be skewed this way. A binomial will always be discrete values, but normal distribution is essentially if we make n really, really big and we have exactly even probability on either side, then we will get something like this as we see in this image, where this is normal distribution and k will be the distance away from the mean. And so there is actually a function to tell you this is the probability density function, and I'll write it out clear here. And so this is the probability density function, and this is what that would look like. But then if we want to find the probability of getting it a value or less, so let's say, oh, what's the probability of getting 1 standard deviation or lower? So lower than a standard deviation away. Then we do the function, the cumulative distribution function, will be the integral from -infinity to x of this density function. And I'll use a x prime, so dx prime. And using normal distributions, when you have a lot of data, a lot of things generally tend to be very similar to a normal distribution. So if there's a typical value, a lot of things will be centered around that value, and then the further away you get from the expected value, the less likely you are, and that will generally look like a normal distribution. Alright, and that is Introduction to Probability. Let me know if you have any questions. I'll be happy to answer them in the comments, and thank you for watching.